Yes and no. If you're talking about radiation, like in the element uranium, yeah, that's dangerous. But radiation as a general term actually refers to anything that spreads away from its source. So optical radiation is just visible light energy spreading out. Okay, so we've got a spectrum of a beam of sunlight, and it looks like the colors bleed into each other. There are no interruptions. Just a band flowing from violet to green to yellow to... you get the idea. Well, what happens if the sunlight spectrum is magnified? Maybe you all didn't do the reading. Well, here's what you'd see. I want you to notice that this spectrum is interrupted by dark lines, called spectral lines. If you really magnify the spectrum of the sunlight, you could identify more than 100,000 of them. They may look kind of randomly placed, but they actually form many distinct patterns. And if you were looking at the spectrum of some other star, the colors would be the same, but the spectral lines would break it up at different places, making different patterns. Each pattern stands for a distinct chemical element, and so different sets or patterns of spectral lines mean that the star has a different chemical composition.
So how do we know which spectral patterns match up with which elements?
Well, a kind of spectroscopic library of elements was compiled using flame tests. A known element, say a piece of iron for example, is heated in a pure gas flame. The iron eventually heats to the point that it radiates light. This light is passed through a prism, which breaks it up into a spectrum, and a unique pattern, kind of like a chemical fingerprint of spectral lines for that element appears. This process was repeated over and over again for many different elements, so we can figure out the chemical makeup of another star by comparing the spectral pattern it has to the pattern of the elements in the library. Oh, an interesting story about how one of the elements was discovered through spectroscopy. There was a pretty extensive library of spectral line patterns of elements, even by the 1860s. A British astronomer was analyzing a spectrograph of sunlight, and he noticed a particular pattern of spectral lines that didn't match anything in the library. So he put two and two together, and decided there was an element in the sun that hadn't been discovered here on the Earth yet. Any guesses about what that element is? It's actually turned out to be pretty common, and I'm sure all of you know it. Okay, let's try something else. Any of you happen to be familiar with the Greek word for sun, by chance?
Something like Helios, or something like that. Oh, it must be helium. So you're saying that helium was discovered on the sun first?
Yes, and this is a good example of how important spectroscopy is in astronomy.
Okay.
What is the lecture mainly about?
Okay, can anyone give me an answer?
就是说通过光确定它到地球的距离，然后还有它的元素。
OK， 还有什么别的信息？那肯定不止这一点儿，还有什么别的信息？把你们所有听到的碎片性的信息都说出来。我知道大家可能现在听不完全，但我想知道能听懂多少。还没有任何别的碎片性的信息都可以。
举一个例子。
说。
我就举一例子，然后说，跟有一科学家，然后根据太阳光的然后那个光谱去确定了太阳里边还有什么元素。
好，崔同学继续补充。
我说好像是说，就是说我们可以根据就是它那个元素燃烧了产生了色儿，产生颜色，然后来确定还有什么有没有我们没发现的问题。
好，来，任永年有没有补充？
说把那个阳光通过三棱镜，然后去放大去观察，会看见在那些颜色之间会有一些比较暗的地方，
好，
暗的地方都是特殊的一些。
行，好，行，大家有数了。行，同学们给你们布置一个作业，今天晚上回家把 TPU3 的最后一篇 lecture 自己听完，就是我刚刚放这个，把文本拉出来当阅读做 ，OK， TPO3 最后一个 lecture， 文本拉出来当阅读做，把所有的单词搞明白，搞明白他讲了几层，怎么流动的这个逻辑。OK， 写一个提纲出来，或者写一个笔记出来也行，做个笔记出来也行。
TPO3是23。
TPO3 的最后一个篇听力
最后。
，TPO3 的最后一篇听力。OK， 明天上午我们讲 lecture 的文章，我会挑几个稍微简单点的 lecture 开始入手，但是你们自己今天晚上要熟悉一下 lecture 都讲什么东西，有多么深讲的。OK， 好的 ，OK，that's all for today's class。明天上午是9点钟，大家都知道吧 ？OK，o'clock。所以我今天作业不多，就把单词查出来积累出来，你们会发现有不少生词的。